Hello and welcome to another video. I've been a bit useless on doing my videos recently, so I'm trying to get back into it. But yeah, here goes. I'm doing Step 1 2004 question 5. This one's quite straightforward really, but I could understand how you might not be too happy with how to represent your solutions. But it's not too bad at all. It really isn't. The maths in here isn't too difficult at all. Okay, they've given us 5 distinct arithmetic progressions. This can be done as well if you're an AS student, if you've never seen arithmetic sequences before, because you've definitely seen nth term before, and really this is about nth term. Now they want us to write down an expression for the value of the general term in each of the 5 progressions. Well, this is obviously 5m minus 4, 5m minus 3, 5m minus 2, 5m minus 1 and 5m. However, I'm going to use different letters for each sequence because we might be, if you read a little bit further on, we've got to show that the sum of any term in B and any term in C is a term in E. Then you can't use n for each one because you're referring to the same term in B and the same term in C, i.e. the 4th term in B and the 4th term in C is a term in E. But they're saying any term in B and any term in C. So we do actually need to use different letters there, and that's really important, and that's probably where a lot of people go wrong on this kind of question. Okay, so I'm going to start by defining things. Let UA be the 8th term in A, let UB be the B term in B, and then I hope the examiners will be happy with me just going ... etc., where A, B, C, D and E are members of the natural numbers. Then we've got UA is 5A minus 4, UB is 5B minus 3, 5C minus 2, 5D minus 1 and 5E. I'm sure I don't need to explain why that is to you. So to prove that any term in B and any term in C is a term in E, yeah, well, and this is why I mean we need different letters here, because if I was saying 5m minus 3 plus 5m minus 2, all I've actually proved then is that if you take the same term positionally in B and add it to the same term positionally in C, like 12 plus 13, they'll equal a term in E, 25. Like, that's not as strong a result as any term in B plus any term in C, is it? Because it could be the 1st term in B plus the 19th term in C. You've got to show that's a term in E, and that's why you need different letters here. Okay, so 5b minus 3 plus 5c minus 2, you know, add it together. You've clearly got a multiple of 5 there after a bit of factorising. I set b plus c minus 1 equal to e, and that gives 5e, which is obviously a term in e. So what you'll probably find with this video is it might just help you with how you represent your solutions a little bit. You know, maybe you don't like the way I represent my solutions. Maybe you've used modular arithmetic in the second part of this question. Well, good for you, seriously, that's brilliant. But I'm aiming this video at people who've never seen modular arithmetic before. But if you haven't seen modular arithmetic before, really it's a great idea to look at it before you do these extension papers, because lots of questions are much easier with modular arithmetic. Okay, so that was pretty easy to prove, yeah, and it's the same with both these statements as well. Prove that the square of every term in B is a term in D. Okay, 5b minus 3 all squared comes to that. We want to show it's in D, so clearly if you're 1 less than a multiple of 5, because that's multiple of 5, that's multiple of 5, and this is 10, that would be a multiple of 5. So we're 1 less than a multiple of 5 here. Therefore, we are going to be a term in D. And setting 5b squared minus 6b plus 2 equal to D gives you that result, which is obviously in D. Yeah, that's the way I would represent my answer here. Likewise, a similar claim for C. 5c minus 2 squared, you get this, which has a plus 4 in the end. We'll call it plus 5 minus 1. And you can see this is also a term in D. So in other words, if we square any term in B or any term in C, we end up with a term in D. Let's quickly practice here. 18 squared is 324. You can see all the terms in D end in 4. None of the other sequences end in 4. In other words, yet when you square 18, you get a term in D, which is 324, because terms in D will go end in 4s or 9s. Okay, so there we go. There's an example of it working. It works the same with terms in B as well. Try it. You know, square 12, you get 144. That's obviously a term in D. Okay, so there we go. That's proved those results. So how are we going to do this question? Well, the STEM's given us a massive hint. Yeah, if we consider, we've already shown that B and C. It's worth pointing out that all of these sequences represent the natural numbers. Yeah. Every single one, because at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I can consider the squares of B, C, A, D and E, I'll then know what x squared finishes with. I'm just going to pause my video because I've given some Sorry about that. That was a minor problem outside with my children. Okay, so where were we? We've just proved these results, and yeah, I'm just talking about how I'm going to prove this. Really, I'm just going to show, because this ends in a 3 and x and y are positive integers, I'm just going to show that after you've squared something and added a member of the E family to it, it can't be a member of C. That's what I'm going to do. So I'm going to point out all members of sequences B and C are members of D after squaring. We've just proved that. For A and D, after squaring, we see that I think they end up being members of A. Yeah, let's have a look. So we've got 5A minus 4 squared, which is 25A squared minus 40A plus 16. That's 4 less than a multiple of 5. So let's write that as 5A squared minus 8A plus 4 minus 4, you know, which is a member of A. And it's the same for D, I think. Oops, let's use D. 5D minus 1 squared is 25D squared minus 10D plus 1, which is 5 times 5D squared minus 2D plus 1 minus 4, also a member of D, a member of A. So what have we shown? Yeah, it's trivially true as well that E squared is a member of E, because we're just squaring a multiple of 5, which is also a multiple of 5. So let's quickly argue that. For E, the squares would also be members of E. Okay, 5E squared is 25E squared, which is 5 times by E squared. Yeah. Okay, so that's proved that. Yeah. So what have we got here? How am I going to finish my argument? Well, let's move this over here. I'm simply going to argue this. I'm just going to say I've got a member of A, D, or E plus a member of E. Yeah. So which is a member of A, D, or E plus E, yeah, because 5y is clearly E. And if you do A plus E, you end up still in A. If you do D plus E, you end up still in D. And if you do E plus E, you end up still in E. Basically, adding 5 to these, you're going to be in the same sequence. So I'm just going to finish that off as my proof. Hence, we can only be in A, D, or E. And so the final digit can't be 3. And I always wonder in these kinds of questions, because the algebra is so trivial, you know, if they don't mind if I start just skipping steps, do they want me to actually show here that, you know, when I add 5 to 5m minus 4, I'm still in the sequence 5m minus 4? Possibly? I don't know. Like, if you want to write in the comments that you think I've been a bit slapdash here as well, feel free, because, you know, I kind of wonder, am I being slapdash and saying this is obvious? Like, you know, is it not obvious I know what I'm doing now? Now, the last bit is a little bit harder, but not that much harder, yeah? We can point out that x squared and y squared are members of A, D, and E. We've already proved that. A, D, E. So, x to the 4 and y to the 4, well, what are they members of? They're going to be members of Well, when you square A, we've already proved that you're in A. When we square D, we've proved that you're in A. And when we square E, it's trivially true that you're also in E. Now we've just got to consider the 2y to the 4. Now if you've got 2y to the 4 for A or E, then you've got 2 times, what was that again, 5a minus 4, which equals 10a minus 8, but let's write it as 2 times 5a. Let's write it as, that's going to be minus 8, isn't it? So I'm going to have minus, I want to take the 5 out as well, not the 2. 5 times 2a. And then I'm going to get like a minus 1 minus 3, yeah? That's a member of C. And if I was to double instead E, well, 2 times 5e is just 5 times 2e, which is a member of E. So what have we shown here? We've shown that 2y to the 4 must be a member of C or a member of E, and x to the 4 must be a member of A or a member of E, yeah? Member of A or E. 2y to the 4 is a member of C or E. Is that C actually, or is that B? I can't remember. I might have actually got that wrong. It's actually B with a minus 3. So, apologies for that slight error. Member of B. Now, what about when we add them together? We do need to consider adding. Thus, x to the 4 plus 2y to the 4 is a member of. Now, if we do this casually in our heads, I wonder if they'd take some marks off for me, but I am going to do it casually in my head because the algebra just is so easy. You can easily write it down yourself, and I suggest you be more paranoid than me in the exam. Right, if you do an A plus B, yeah, you're always going to be in C, aren't you? 1 plus 2 is 3, 6 plus 7 is 13, 11 plus 12 is 23. It would be trivially true to prove it all like all the other ones were proved. So in other words, A plus B, you're going to be in C. But if you did A plus E, you'd still be in A. If you did E plus B, you'd be in B. And if you did E plus E, you'd be in E. But you definitely can't be in D, yeah? And therefore, the final digit cannot be a 4. Because the final digit being 4 is a member of D. So, x to the 4 plus 2y to the 4 equals blah blah blah, ending in a 4, to 26081974. Is insoluble in integers. There we go. And really what they're teaching you here is modular arithmetic without modular arithmetic being mentioned. That's what we're really doing. We're basically working in like mod 5 here. But yeah, really interesting question, quite an interesting question. Anyway, it gets a bit tedious with the algebra though, but it's not difficult. I hope you found that useful. Well done, and keep up the good work. Bye bye.